All right, so hi everybody. As Gaussian said previously, I'm a PhD student here at Lund University, and my supervisor is Jonas Vedin, and this is joint work together with Jonas and Gaussian on deriving strong rules, a strong screening rule for slope. So Patrick already talked about the screening rule for lasso, and I will reiterate some of what he said with a little bit of a different notation. But I'm going to start by reintroducing the slope problem. So as we know, the slope estimate is a minimizer to a composite objective of some differentiable part and then the slope norm. And in particular for this talk, we are interested in fitting a path of regularization penalties. So basically what we want to do is we want to start with a penalty that is large enough to penalize every coefficient in the solution so that it starts at a null model, so a model with only the intercept, and then increasing the penalty throughout the regularization path to one by one start to introduce the coefficients into the model. And the reason why we do this is often that we want to cross-validate to tune our lambda. So for many problems, we don't know how to select lambda in this problem. So for the parameter here in the penalty, we don't know how to select lambda, and that's why we're interested in doing a regularization penalty. And now the motivation for predictor screening rules in general is that we already know from the start, from the get-go, that many of the coefficients along the regularization path will be sparse. So many of the coefficients will be sparse, which means that the columns of X, the predictors in X, will be inactive. So that actually we can solve a much smaller problem and still solve the whole problem, so to speak. And the basic idea here is that what if we could introduce a relatively cheap test to determine which predictors are inactive before even fitting the model. If we're able to do so, then we can discard those predictors, fit the model to the smaller set, and be done in the fraction of the time required otherwise. And as Patrick described earlier, it turns out that we can, and roughly speaking, there are two types of screening rules available. Either the safe rules, which provide a certificate that whatever predictors we decide to discard will in fact be inactive in the end. Or we have heuristic rules as well, which are a rule of thumb to discard predictors. And it is possible that we discard predictors erroneously, producing violations with the heuristic rules. But it turns out, and will turn out, you will see later, that this is actually not a big problem. To get to the strong rule for slope, I'm going to start with the strong rule for the lasso. Again, we're solving a similar problem, but this time we have a different penalty, the regular lasso penalty. We have KKT stationary condition. It looks like this, which says that the zero is somewhere inside the sum of the gradient of the derivative part and the subgradient. The subdifferential for the lasso part looks like this. So we're saying that if we have a coefficient that is zero, then we will have the subgradient will be somewhere in this set, and if it is non-zero, then it will be the sine of beta. It should be a y here, right? We say the sine of beta times lambda. And this, of course, means, as Patrick showed, that if we can prove that this is a fact, then we can, if we have this relationship, then we know that beta I is going to be zero at the solution. But of course, for all our problems, we won't know this part, particularly not if we're along the regularization path. We'll have the gradient at the previous value, but not the gradient at the current value. This is our basic problem, right? But what if we could predict what the gradient is going to be at the next step of the regularization path and replace that part with or actually replace the true gradient at that solution with some sort of estimate, some sort of, somewhat conservative estimate in order to assure that we don't get too many violations. Then apply this KKT stationarity criterion, which is not really a KKT criterion anymore, but and use that as a prediction of the sparsity, basically, the sparsity of the coefficients at the solution. The question is only what kind of estimate would we use to do this? It turns out that we can use something called the Unislope bound that Patrick also described earlier, but I will briefly cover here again. This is simply the difference between the previous penalty strength parameter, lambda, and the current penalty strength parameter. And we are assuming here that we are decreasing going through the regularization path, so that we are always decreasing lambda as we go. This is a graph where we have the gradient at the y-axis and then the penalty strength at the x-axis. And whenever we are on the unit line, or actually, I should say, wherever you're below the unit line, we know via the KKT stationary criterion that any predictor, any coefficient with a value below this line is going to be 0. Okay, now assume that we are at this point here. And now we're going to say that if we assume that the gradient is a function of lambda, and assume that it is piecewise linear, the most that it is going to be able to increase is by a unit slope of 1, a slope of 1, which means that it can reach no further than this point over here. And if this point over here is not this point, but something below this point, and we see easily that it cannot reach this line in time for the next penalty. So moving from this point to that point, this one is either going to be able to reach it or not be able to reach it. And that is the basis for the strong rule. So we're saying we're going to discard the predictor if the gradient is smaller than 2 times the current lambda minus the previous lambda. What this really is the previous gradient plus the unit slope bound, which is equal to gradient projection, and we're checking that against the current lambda. And this turns out to be extremely efficient. And Tipshirani and their paper show that, particularly for the regime in which we have a lot of predictors and few observations, we can fit the model, the lasso model, in just a fraction of the time, maybe more than 10 times as fast as we do otherwise. And this is quite remarkable. And in fact, it's kind of funny, right? Because you wouldn't assume that solving ridge regression, solving the lasso would be faster than solving ridge regression. But in fact, using the GLMNet package, that is mostly the case, due to the fact that we can discard predictors. And even more remarkable, perhaps, is that sometimes solving an entire path of lambda can be faster than solving for a single lambda. And in fact, if you run GLMNet by default, even if you supply a single lambda, then GLMNet is going to fit 5 lambda for you. So I'm not talking about GLMNet now, I'm talking about the popular package that was introduced together with the lasso, basically, or not really introduced together with the lasso, but is one of the most popular packages for the lasso. What can this look like in action? Well, here we have a set of coefficients. This is the same graph that Patrick showed earlier. We have the gradient over here, the penalty path, the penalty over here, and we're moving from right to left through the regularization path. And now we are looking at this lambda over here, k minus 1. That is the previous solution, or previous step, and moving to step lambda k. Using the strong bound, we're basically going to say that we're basically going to check how far can these predictors reach, testing the unit bound. And every predictor where this line doesn't reach the unit line over here is going to be discarded. And in this case, this means all of these predictors are going to be discarded. And for this particular example, we only have this predictor over here, this coefficient over here, this coefficient over here, and this coefficient over here that escapes the strong bound. All of the other ones are not going to be in the model we fit. But as it turns out, for this example, we should give you a hint of what the strong rule is capable of. None of the other predictors are in fact, or there are no violations here. All of the predictors are in fact going to be 0 at the next step, since none of these reach the unit line. And now we get to the strong rule for slope. It turns out that we can make exactly the same kind of argument here. So we are going to use the subgradient again, and I know that this is a lot of heavy notation, but starting with this part here, this defines a cluster that contains the indices of coefficients equal in absolute value. So sometimes this is called an equivalence set. Some authors use that notation. This is a ranking operator that returns ranks of elements in X, actually elements in X, absolute value X. And then we also have, so we're letting the absolute value here not be the cardinality of a set, but instead be a vector with all its elements set to the absolute, the magnitudes. And this notation over here returns the absolute values of X sorted in non-decreasing order. And we also have a cumulative sum here that is vector valued. So this is not just the last cumulative sum, but all of the cumulative sums of this expression inside here. So just as we did with the subgradient for lasso, we're going to say that if a coefficient is, of all the coefficients in a cluster are equal to 0, then the gradient or the subgradient is S in this space for which this condition holds. So we're taking the cumulative sum here of differences of the sorted S absolutes minus a subvector of lambda. We're going to check that each of these elements are less than or equal to 0. And if beta, the cluster of betas, or if a cluster of betas are not equal to 0, then we'll say again that this part has to hold once more. We're also saying that the last of the cumulative sums, that is the sum of all of these, of this expression, must be 0. So it's not vital that you understand exactly how this works for the rest of the talk. But I've put my slides up again if you want to move back to this. Now I'm going to move on to the algorithm we use in practice, because it turns out that it is not as easy to apply the strong rule for slope as it is for the lasso. So here we have to use an algorithm to do this. We're going to start by setting C equal to the absolute value sorted in decreasing order of the predictor. That should be at the lambda k, and plus the difference between two lambda vectors. So notice now that in the compared in contrast to the lasso, these are sequences now. So lambda k minus 1 is a sequence of lambdas, and lambda k is also a sequence. Then we're going to set lambda to be lambda k, the current lambda. And then we run the algorithm. And in the algorithm, we're going to use two sets that start at empty, and then we move through the ordered. So remember that C here is this part over here. So we've ordered a sequence of our gradient prediction. And moving through, we start with the empty set, and then moving through from 1 to P, we start by inserting. So there's an index corresponding to a predictor, basically. We're going to start with the predictor with the largest absolute gradient. We introduce this index into B, then we check. For this part, we check the cumulative, or check the sum, sorry, if it is larger or equal to 0. And we're going to add this part into set S. and reset B. And then we move on through all of the predictors, checking the condition, each one by one. And at the end, we are going to return the set S, which is going to contain the active set. So using this, we're going to return the active set, and then we only have to reorder the result based on the ordering of the gradient prediction. And then we're done. Then we have our active set. This is a little bit of more work, and it is somewhat more computationally intensive, expensive compared to the lasso estimator. But it turns out that that doesn't matter. The results are still very good, as we will see next. These plots show some results for a Gaussian design. We have a 200 by 5,000 matrix here of predictors. And we have correlated each predictor with each other predictor with the correlation of rho. We're starting with small correlation and then increasing it as we go on. And we see already that at low correlation, the rule is extremely efficient. We're basically discarding all of the other predictors down to the straight line over here. So the dashed line corresponds to the true active sets of the estimates. An interesting part here is what happens when we increase correlation even more, though. So what happens is, this is related to the slope problem itself, is that if correlation is high, then instead of having few variables enter at the start of the path, we have a spike of variables, predictors entering, although they do so in a few clusters. And then we have a decreasing number of coefficients until the end, which is kind of interesting. But it also means that it also shows that the strong rule is more conservative at this end, including a little too big part of the predictors. This is what it can look like for real data. So here we have 4 data sets. We've transformed the outcome here to work for both ordinary least squares regression, regularized with the sorted L1 norm, and logistic regression. And for all these data sets, this works extremely well. Looking down at, for example, the Dorothea set, which consists of 89,000 predictors, we only have a very, very small fraction over here. So at the y-axis here, we have the fraction of predictors. So these are all of different sizes. It's possible to incur violations. We know that from the strong rule from lasso, and that holds here as well. We have a few more requirements or assumptions. For instance, we have requirements that the order of the coefficients, order of the gradient, isn't changing between lambda k minus 1 and lambda k. But even despite of these assumptions, it turns out that violations are very rare. In this graph, we've run benchmarks against the problem with a predictor matrix of 100 by P, increasing P for the different panels. And basically for many of the examples here, we don't run into any violations at all. And even for the examples where we do, this represents the fractions of the y-axis here, represent the fractions of fits where we have any violations, which is in the order of single digits, so around 1% at this part of the path, and so on. So the number of refits we have to do are very few. And each refit is going to cost a check of the KKT conditions and then a refitting of the entire model. Since the estimates at that point are going to be very good warm start for the next problem, that turns out to not be a big problem at all, since we are solving almost the same problem. In terms of performance, it turns out that these rules work well as well. Here we have solved a slope problem using the screening rules for 4 types of families: multinomial, Poisson, logistic, and OLS. This is actually, sorry, this should be the other way around here. So we have 200 times 2k. The timings here are on the log 10 axis. So, and all of the blue boxes represent time spent using the screening rule, and this is the time using no screening rule at all. And it is clear that we are improving performance by a lot, usually by at least a factor of 10. The problems here are problems where we have correlated each column with the next one with a correlation of whatever it says over here on the y-axis. I think maybe I'm out of time, so I might skip the part of the algorithms. Could anybody advise me on if I should do that or not?
Well, maybe yes. Maybe we
Yes.
would like to finish like in 1 hour. Yeah.
Yeah. We're going to some limitations of this. Some of the parts we use here, or some of the assumptions we use here, are the unit bound assumption, and that turns out to be actually very conservative, right? It's a conservative assumption to assume that the slope increases by 1, and that is what we can see as well in, for instance, the example where we have a lot of correlation between predictors. Another part is that we're not using second order structure in any way. So we're only using the gradient, although we, of course, have the Hessian available for most of the problems. And for instance, for OLS, the Hessian is not even that prohibitive to use in computing. Also, current methods of slope don't really make as good use of these screening rules as, for instance, coordinate descent does for the lasso. Those are some of the problems. In any case, we have introduced these rules into our slope package for R, which you can find at the address given here. And apart from introducing these screening rules, we also have support for, as you could see in this presentation, least squares regression, logistic, Poisson and multinomial models regularized with the sorted L1 norm, and also support for sparse and dense predictors, cross-validation, and everything has also been recently transported from R to C++. The package runs pretty fast. And in addition, we currently have a Google Summer of Code student working on the package, and I hope we will be successful in implementing a proximal Newton solver for slope this summer. Anyway, thanks for listening. That was all I had to say today.